Hello, good morning, good evening, good afternoon, everybody, wherever you might be. I'm very happy to welcome my mathematical brother from Maryland, Jonathan Rosenberg. He will blow us away with non-commutative geometry and duality of Orientifold field theories. Jonathan, the Zoom is yours. Take it away.
Okay, thank you. Is the volume okay? Can you guys hear? So thank you very much, Piotr, for organizing this wonderful seminar. I don't go to it as often as I should because it sometimes conflicts with other things going on, but it's really great service to the mathematical community and really appreciate it.
Thank you.
So I wanted to talk about some use of non-commutative geometry for some applications to mathematical physics. And let me just start with a little review of a few ideas from string theory, even though that's not really what I'm going to talk about, but that provides a little bit of motivation. So in string theory, we replace point particles by one-dimensional strings, hence the name. And these strings they're like one manifolds that are moving in space-time, and they are really, really small. So on the order of the Planck length. So this is, there are a lot more orders of magnitude between the radius of the proton and the Planck length than they are between our macroscopic world and the radius of the proton, just to give you an idea. So it's a really, really small number. But anyway, so these strings moving out in time trace out a two-dimensional surface, which is called a string world sheet. And so in string theory, we study maps from the string world sheet into the space-time manifold X. And this is the sort of classical, semi-classical version of this, and then we sort of use this to make a quantum theory. So the hope is that string theory would provide some way of combining gravity with the other forces of physics and with quantum mechanics. In most physical theories, we have a collection of things called fields, and there is something called a Lagrangian. Then by integrating the Lagrangian, you get something called the action. That's this S over here. And then the principle of least action says that you sort of expect behavior near the critical points of S. Now, in the quantum theory, of course, quantum theory is not completely deterministic. So actually what you do instead is to take a path integral over the space of all possible field configurations, and then there's a path integral that involves this action. But anyway, that's the sort of basic idea. So let's say phi here is one of these strings moving in time. So it's a map from this string world sheet into X. And then the leading terms in the action look like this. So there's a term that involves, here I'm doing things in a Euclidean signature. So X really should be a Lorentz manifold, but let's just take it to be a Euclidean manifold just for simplicity. The physicists often do that. So, so here we take the gradient of phi and integrate the norm squared of the gradient. And then the critical points for this linear functional are what are called harmonic maps. So harmonic maps from sigma into X. And then there's also another term in the action that involves pulling back a two form on X back to sigma and integrating. That's called the Wess-Zumino term. So this B, this two form on space-time is called the B field. And then this constant over here is the string tension. The B really is only locally defined, but it has a class in H3, which is called the H flux. And then there are also terms involving gravity that involves the curvature of the metric on space-time. And then there are also terms, gauge fields that correspond to the fundamental particles, both bosons and fermions, and usually require some kind of supersymmetry. So the theory involves both bosons and fermions and their symmetries that exchange them. All right, so that's a basic setup in quantum field theory. But not every classical sigma model. So this thing back here is called a sigma model because we're integrating this action for maps out of this sigma here.
Sorry, I have a question.
Yeah.
So you mentioned that after all, one takes some kind of functional integral over all these possible, not paths, in fact, but something like that. So is this measure somehow precisely defined, or is it only on the heuristic level?
Well, it's basically on the heuristic level, but I mean, physicists don't worry about that so much, but mathematicians do. Yeah.
Okay. Thank you.
Anyway, we're not going to need that anyway, so it's not going to be relevant. So, but what does happen is that this classical sigma model, which is what we have over here, doesn't always quantize well, and in order for that to happen, certain anomalies have to cancel. And anomaly cancellation in superstring theory requires that the dimension of the space-time be 10. And since ordinary observable space-time is R4, which is four-dimensional Minkowski space, usually require the space-time manifold X to be R4 across some 6 manifold. Okay, and the 6 manifold could be compact, and the sort of observable part of the space-time is this R4 over here. Now, usually you want at least n equal 2 supersymmetry, and one way to get that is to take this M over here to be a complex scalar manifold. All right, it has 6 real dimensions, so that means it has complex dimension 3, and you want it to be what's called a Calabi-Yau manifold. That means the first Chern class is 0, and so M admits an everywhere non-vanishing holomorphic 3 form, and that's used to construct some of this extra supersymmetry. So this M is called a Calabi-Yau manifold, as I said. And in this talk, I'm mostly just going to talk about the very simplest case, which is a case where M is just C2 cross an elliptic curve. Okay, so an elliptic curve is an example of a Calabi-Yau manifold. That's the simplest non-trivial complex manifold with vanishing C1. Now, there are different versions of superstring theory, and we're mostly going to talk about types 2A and 2B. And the difference between them involves the chirality conditions on the fermions. In other words, the handedness of the left and right moving spinors. But I haven't told you about the fermions, so again, you can sort of ignore that, except for one basic thing, which is that these two theories emphasize different aspects of the geometry of the Calabi-Yau. So one of these involves the symplectic geometry of M, and the other involves the holomorphic geometry. So the 2B theory involves the holomorphic geometry, and the 2A theory involves the symplectic geometry. And the string theories tend to come in what are called mirror pairs, where you have a mirror symmetry that interchanges the Kähler and the holomorphic geometry. So when M is C2 cross an elliptic curve, not much is going on the C2, because this is sort of trivial. So the complex geometry of an elliptic curve is given by a parameter tau in the upper half plane modulo the action of PSL2Z by linear fractional transformations. And the Kähler geometry in the B field also combine to give a parameter in the upper half plane, which again is only defined modulo PSL2Z. So here B is the B field that I talked about before, and K is the Kähler form. So this is a complex 2 form over here. And when you integrate it, you get something in the upper half plane, and then the mirror symmetry just interchanges the tau and the rho. So tau is the complex parameter, rho is a Kähler parameter. Another thing about string theory is that physicists talk about both closed and open strings. So a closed string is compact without boundary. So that's just a loop, in other words, it's like a circle. And an open string is a compact manifold with boundary. So it's like a little interval. And in order to get a reasonable theory for the open strings, you need to impose boundary conditions, usually Dirichlet, sometimes Neumann boundary conditions on the places where the boundary of the string ends up. And these submanifolds where the boundary of the string ends up are called D-branes. So this is the usual physicist terminology. D stands for Dirichlet, because we're talking about Dirichlet boundary conditions, and brane is short for membrane, which is a kind of another word for a manifold. So these D-branes in type 2b are even dimensional and are basically complex submanifolds of X. And in the 2a theory, they're odd dimensional. And then they might be, for example, Lagrangian submanifolds for the symplectic structure. And in either event, the D-branes carry certain Chan-Paton bundles on them. And there are topological charges associated to the non-triviality of these bundles. And the classes of the bundles push forward under the Giesen map to charges that live in the K-theory of space-time. And so you get classes in even-dimensional K-theory for type 2b and odd-degree K-theory for type 2a. And there are also some other charges called the Ramon charges in the K group of the opposite parity. Okay, now, so I mentioned mirror symmetry, and mirror symmetry is believed to originate from a more elementary kind of string theory duality, which is called T-duality. And that sort of arises the following way. So suppose you have 2a or 2b string theory on a space-time manifold X, and you have the B field, which gives rise to this H flux. This is an integral class in H3. And suppose your space-time X happens to be a circle bundle over another space Z. So then there is a dual theory, which lives on a sort of dual space-time, which is also a circle bundle over Z, but has a dual H flux. And roughly speaking, the circles in X, so those are the fibers of the fiber bundle from X down to Z, are replaced by the dual circles, and the type of the string theory is flipped also. So if you start with a 2a theory on X, you get a 2b theory on X dual, and vice versa. And the T-duality also interchanges the winding and momentum modes in the action. But the D-brane charges in the two theories have to match, so it turns out the D-brane charges get twisted by this H flux. So you get a class in twisted K theory of X, and a dual class in twisted K theory of X dual for the dual H flux. And you need to get an isomorphism like between these two things. And the question is, from a mathematical point of view, where does that isomorphism come from? And about 10 or 15 years ago, Matai Varghese and I studied this, and we discovered that this isomorphism of K-theory groups actually comes out of an application of Kahn's Tom isomorphism theorem for actions of the reals on C-star algebras. So there's an action of R on a C-star algebra attached to X and H, and when you take the cross product, you get something that's Moridi equivalent to this, and there's a shift in degree in the K-theory by 1 because of the Tom isomorphism, and that gives a very satisfactory explanation for this isomorphism. So I want to, in general, discuss more general dualities and how these various dualities of string theories originate from various kinds of K-theory isomorphisms that come from non-commutative geometry. So that was just one example. Okay, maybe I should pause at this point and see if there are any further questions before we go on.
I don't see any raised hands.
Okay.
Yeah.
All right. So let me go on here and let me talk about the Baum-Kahn conjecture for a moment. So I assume, you know, given the audience in this seminar, most of you already know about this, but I just want to mention that the Baum-Kahn conjecture arose out of many different sources, none of which have anything to do with what I'm talking about. So here are some of the original motivations for it. Rigidity properties in manifolds with large fundamental group, like Mostow rigidity, the Borel conjecture, index theory for equivariant elliptic operators, harmonic analysis on discrete groups, and calculation of the K-theory of certain C-star algebras. So all these things were part of the motivation for the Baum-Kahn conjecture, and it's just kind of serendipity, it seems, that it also turns out to be relevant for what I'm going to be talking about in this talk. So just to sum up what the Baum-Kahn conjecture says in the simplest cases, it says that if you have a group G, let's say it's a discrete group, and you take its real or complex group ring and you take its reduced C-star completion, then the K-theory of this reduced C-star algebra of G should be computable just from topological properties of G. In particular, if G is a torsion-free discrete group, then you expect an isomorphism from the KO homology of BG to the KO K-theory of the real group C-star algebra, and similarly with a complex K-theory. So here BG is the classifying space of G, so that's the topological space whose homology is precisely the group homology of G. Okay, so this is very close to the group homology of G, so that's certainly a topological type invariant, whereas this thing is defined analytically. Now let's look at an example. Suppose you take G to be the integers. Classifying space is just a circle. The group C-star algebra is the continuous functions on the Pontryagin dual, which is the continuous functions on the circle group. So the complex K-theory of BG is the K-theory, K-homology of S1, and the K-theory of the group C-star algebra is the K theory of C of this circle, which is the K cohomology of S1. Okay, so we get an isomorphism from this to this. And what is that isomorphism? Well, it's just basically a combination of the Fourier transform and Poincare duality. There's a Poincare duality involved because here we have homology and here we have cohomology. Okay, now the real case is a little more interesting. So suppose you work over the reals instead, then the real group C-star algebra is not the real valued functions on the circle, because if you take a real valued function and you take its Fourier transform, you get something that satisfies this, this condition with regard to complex conjugation. So you get functions on the circle such that the function of Z hat is Z bar, the complex conjugate, is the complex conjugate of f of Z. So in terms of the language of Atiyah's KR theory, which I'll talk about in a moment, the KO theory of this group C-star algebra then is not KO cohomology of the circle, but it's KR cohomology of what's called S11, which is the circle with the involution on it that sends a point in the circle to its complex conjugate. And so the Baum-Kahn conjecture amounts to an isomorphism between the KO homology of S1 and the KR cohomology of this S1 with this non-trivial involution. And notice if you didn't take the involution into account, then this wouldn't work, because you rapidly check that you get the wrong thing, because KO lower 1 of S1 has torsion, and for the torsion to match up, you have to use this KR theory, not KO. Okay. All right, so let me go on here. Now, if your group has torsion, then you have to, the right-hand side of the Baum-Kahn conjecture, in other words, the group C-star algebra is the same, but the left-hand side has to be slightly modified. So instead of taking the K homology of BG, you take the equivariant K homology of E underline G, where this is the universal proper G space. So here's an example that we'll use later. Suppose G is a semi-direct product of a finite group and the integers. So let's say you have a finite group H with an automorphism, and the integers act on H via that automorphism. So then the universal proper G space will just be a space in which H acts trivially and the integers act by translation on the real line. And then, okay, so that's what you would get over here. And then also there's the Baum-Kahn conjecture with coefficients. So there, instead of just having the K theory of the group C-star algebra, now on the right-hand side, you get the K theory of a cross product, reduced cross product of some G C-star algebra A by the action of G. And on the left-hand side, you get the equivariant KK group for functions on E underline G. That's what this thing is. And A in the second variable, where A is A is the coefficients, so it's just some C-star algebra with an action of G on it. Okay, now, as I said, we're going to need a variant of K theory, which is called KR theory. So the R stands for real. So this was introduced by Atiyah in a famous paper, K-theory and reality, in 1968. And it's a kind of a K-theory defined on the category of real spaces, which are locally compact spaces equipped with an involution. So an involution on a space just means a self-homeomorphism whose square is the identity. And the reason for the term real and the motivating example is the case where your X is the space of complex points of an algebraic variety that's defined over the reals. So if you have a set of polynomial equations over the reals, there may not be any real solutions, but there are always complex solutions. So that's what this X is. And then on that X comes equipped with a canonical involution, namely the action of complex conjugation. So that's the action of the Galois group of C over R. Okay, so this connection to real algebraic geometry is why Atiyah called this real K-theory. Now, when you have a compact real space, KR of X, the involution will be implicit, is the Grothendieck group. Well, ordinary K-theory is the Grothendieck group of vector bundles, right? So here we take the Grothendieck group not of complex vector bundles, but of what are called real vector bundles. So what's a real vector bundle? It's a complex vector bundle over X together with a conjugate linear involution, which is compatible with the involution on the base. So if the involution on the base is trivial, that means that you're just doing conjugation, complex conjugation pointwise. And so then a vector bundle E equipped with this kind of a conjugation is just the complexification of a real vector bundle. So this is just the same thing as ordinary real vector bundles with a lowercase r, and then this capital KR just reduces down to real K-theory. On the other hand, you can get back complex K-theory from KR, because if you take a space X, then a complex vector bundle on X is the same as a real vector bundle in this sense on the disjoint union of two copies of X, where you take the involution that just interchanges the two copies. Okay, so this KR specializes to KO in some cases and specializes to complex K-theory in other cases. And so it basically encompasses both of those together, and it turns out this KR theory turns out to be aperiodic. So you can recover ordinary Bott periodicity even in real K-theory from this KR theory. So that's all found in this classic paper of Atiyah, which is very much recommended. Now, the connection between KR theory and physics comes from looking at what are called Orientifold theories. So an Orientifold theory is it's like a string theory where the space-time manifold is equipped with an involution, and you require the maps from the string world sheet into X to be equivariant for a canonical involution on sigma, which is called the world sheet parity operator, and this involution on X. And then the Chan-Paton bubbles on a D-brane have to be real vector bundles in a way that's compatible with this involution, and so the D-brane charges live in basically the KR theory of Atiyah. Okay, questions up to that point? All right, so I guess we can go on. Now, here's a little catch. This involution doesn't have to be free, and in general, there are going to be parts of the space-time that are fixed under the involution. And these fixed sets for the components of the fixed set for the involution are called O-planes. O stands for Orientifold. They don't really have to be planes. They could be just submanifolds. But so you have these submanifolds where the involution is trivial, and these O-planes carry charges which have the following interesting property. So on an O-plane, the restriction of the Chan-Paton bundle, which lives on all of X, has to be carried back to itself under the involution. And so there turns out there are two kinds of O-planes that can arise in physics. They're the ones where the O-plane carries a real vector bundle. Then you get a class in KO, or there can be cases where the O-plane carries a symplectic bundle. And those are called, we'll call those O- planes. Okay, so the O-planes come in two types. There's the real kind and the symplectic kind, depending on how the involution behaves on the vector bundle. Now, let me say a little bit about dualities in KR theory and about some notation. So the simplest manifolds with involution are what we'll call RPQ. So RPQ is it's a real vector space of dimension p plus q, where the first p coordinates are fixed under the involution, and the last q coordinates, the involution acts by -1. So it's sort of like complex conjugation on RP direct sum I times RQ. Okay, so P is the number of pluses and Q is the number of minuses. And then inside there, you can take the unit sphere in that real vector space, and that gives you a unit sphere of dimension P plus Q minus 1. Okay, so this is a TIA's notation. I'm not sure it's the greatest notation, but we're sort of stuck with it for historical reasons. So SPQ means the unit sphere in RP plus I times RQ, where the involution comes from complex conjugation. And so, for example, S10 is 2 points with trivial involution. That's the unit sphere in R, which just consists of the points +1 and -1. And S01 is 2 points on the imaginary line, which under complex conjugation are interchanged. So S01 is 2 points which are interchanged under the involution. And if you take S01 cross X, that's just a disjoint copy, 2 disjoint copies of X with an involution that interchanges them. And as I mentioned, the KR theory of that is just the complex K theory of X. Similarly, if you take S02, so this is the unit sphere in R2 with the involution that acts by -1. So this is a circle with the involution that sends each point to its antipodal point. Then the product of that with X, if you take its KR theory, you get what's called the self-conjugate K theory. And then if you look at the Orientifold theories on circles, the circles SPQ with P plus Q equal 2, so you find the following T dualities. So 2B theory on S20. So S20, once again, is the circle with trivial involution. So this is the D-brane charges for that just live in ordinary KO theory of the circle. So this thing is T dual to the 2A theory on S11. S11 is the circle with the involution that you think of the circle as the unit circle in the complex plane, and the involution is complex conjugation. And so these two theories are dual to each other, and the isomorphism of the relevant K groups arises as follows. First, you go from the K theory of S1 to the KO homology of S1. Notice with this degree shift. So in Poincare duality, cohomology in degree P is dual to homology in degree, the dimension of the manifold minus P. Okay. S1 is one-dimensional, so that's why you have a 1 minus star here. So whatever the degree is here, it goes to 1 minus that over here. So this is Poincare duality. And then you can use the Baum-Kahn isomorphism for S1 for the group of integers. And as we mentioned, that ends up exactly in here. So this composition of Poincare duality and the Baum-Kahn isomorphism gives you this T-duality of Orientifold string theories. So this isomorphism of K groups where the brane charges live is accounted for exactly by certain standard constructions in non-commutative geometry, namely Poincare duality, which is discussed at great length in, for example, Kasparov's original paper on KK theory. He explains how to set all of that up. And then the Baum-Kahn isomorphism over here, in this case for the group of integers. Notice for Orientifold theories, everything's much more interesting than it is if you don't have the involution, because you have all the complexity of KR theory coming in. So here's another example. Suppose instead of S20, this is the circle with the trivial involution, you took S02, that's a circle with the antipodal map as involution. That's T dual to a theory on S11 again, but this time the O-planes now have to have opposite charge. So you have one plus O-plane and one minus O-plane. In S11, this is the circle with the involution given by complex conjugation. There are two fixed points for the involution, +1 and -1. So if you give +1 the plus sign, and you give -1 the minus sign, that's this thing over here. And there's an analog of KR theory with that takes these signs into account. And that's what matches up with what you have on the other side. So now let's talk about where this KR theory isomorphism comes from. And now you'll see a little more interesting non-commutative geometry coming in. Well, why is there non-commutative geometry? This theory over here with a plus and a minus means that over one of these O-planes, you have something attached to the reals, but over the other one, you have something attached to the quaternions. And since the quaternions are non-commutative, you automatically have non-commutative geometry coming in. All right. So the KR theory of S02, this is the circle with the antipodal map as involution, is what's called the self-conjugate K theory, which was introduced by Green and Anderson. And that's periodic with period 4. So you get the copy of the integers in dimension 0 and 1 mod 4. You get nothing in dimension 2 mod 4, and you get cyclic group of order 2 in degree 3 mod 4. On the other side, you have the K-theory of a non-commutative real C-star algebra. So it's almost like what we had before, but now we need a copy of the quaternions, as I said, over the point -1. And you can get that by looking at the group C-star algebra of the following funny group. So this is a semi-direct product of a cyclic group of order 4 by the integers. So let's take the group on two generators A and B, where B generates this cyclic group of order 4. So B to the 4th is equal to 1. And when you conjugate B by A, you end up with B inverse. Okay?
Mhm.
So this is a very simple solvable group. It has a center which is generated by B squared, right? B squared is commutes with A. If you look at this relation over here, you can quickly see that. So B squared is central. So in any irreducible representation of G, B squared has to go either to 1 or to -1. If B squared goes to 1, then you can divide out by B squared, and then this group isn't very interesting. So we're not interested in that summand. So we're therefore interested in the part of the group C-star algebra where B squared goes to -1. Now, if B squared goes to -1, then the relation that you have over here, together with the fact that B squared is equal to -1, shows you that you get a copy of the quaternions. Right, you see that from these relations here? So this is like the relation that the generating relations of the quaternions. And the isomorphism of twisted KR groups corresponding to the T-duality turns out to be exactly given by the real Baum-Kahn conjecture for this funny group G. So this is a kind of, you might say, unexpected application of the Baum-Kahn conjecture. I mean, you might say, well, this is not a very interesting group. It's just like a semi-direct product of a cyclic group by the integers. But nevertheless, the real group C-star algebra is definitely non-trivial, and that's what accounts for this isomorphism over here. So this summand of the group C-star algebra where B squared is equal to -1 turns out to be exactly what corresponds to this Orientifold over here. Now, let me move on to the case where the space-time is an elliptic curve crossed with R8. Well, nothing's going to happen because of the R8, so we're just basically going to ignore that. But since we want the space-time to be 10-dimensional, E is an elliptic curve, so that's a complex torus of real dimension 2, complex dimension 1, and we have this trivial R8 factor. So these E's are the simplest examples of Calabi-Yau manifolds. And R8, as I said, we'll ignore because Bott periodicity has period 8, so multiplying by R8 doesn't do anything to K theory or KR theory or anything else. Now, just one little point here. An elliptic curve is a algebraic curve of genus 1 equipped with a base point. That base point becomes the 0 point for the group structure on E. But having a base point in space-time is rather unnatural. That violates Mach's principle. So really, you should think of your elliptic curve here as just being a principal homogeneous space for an elliptic curve, without a fixed choice of base point. Anyway, to get consistent Orientifold string theory on an elliptic curve, you need to take the involution to be holomorphic in type 2b and anti-holomorphic in type 2a. And since elliptic curves are algebraic, the case 2a turns out to be the same thing as a smooth projective algebraic curve defined over R. It'll be an algebraic curve of genus 1. Now, elliptic curves in complex analysis are classified by the J invariant. And you have a real structure, in other words, one of these anti-holomorphic involutions, exactly when the J invariant is real. And there's a famous theorem of Harnack from the 19th century that if you have a smooth projective curve of genus G with a real structure, then the set of real points has number of connected components, which is called the species, which can be any number from 0 up to G plus 1 inclusive. So since we're taking G equal to 1, you can have species 0, species 1, or species 2, but nothing else. This is called Harnack's curve theorem. So here's the picture of the moduli space for type 2a elliptic curve Orientifolds. And the 2b picture is exactly what you get by flipping this. So there's the tau plane that classifies the J invariant, and then there's the rho plane that classifies the Kähler structure. And you see, if you want to have a real structure, the J invariant has to be real, which means you have to lie on this little locus in the tau plane. Over here, you can get species 0 or 2. Species 1 you can only get on this part. And then this is the dual. And mirror symmetry, remember, flips the tau plane and the rho plane. Okay, now let me get into something that's a little more current. So physicists, including Sognotti, Witten, Gao, and Hori, had conjectured that the Orientifold theories on elliptic curves should break up into 3 groups, and all the theories in each group should be related to each other by T-dualities. And they gave various physical arguments for that. And in joint work with Chuck Duran, Stefas Mendes-Diaz, we set out to see if that's indeed the case and to find explanations for these groupings using algebraic geometry and algebraic topology. And we came up with exactly the same list that the physicists had gotten and kind of nice explanations for what was going on. So here are these T-duality classes. So there turns out there are 3 classes. This one has 3 theories in it. This one has 3 theories in it. This one has 4. And here, 2b with trivial involution b equals 0, trivial B field. This is what's called the type 1 theory. 2b theory with trivial involution and non-trivial B field. This is what's called the type 1 theory with no vector structure. That was introduced by Witten. And this 2b theory with a free involution is what's called the type 1 tilde theory. And then there are various Orientifolds with non-trivial involutions. Here you see the charges of the O-planes. If you have a non-trivial holomorphic involution on an elliptic curve, and there are really only three possibilities. Well, you can have a trivial involution that doesn't do anything. You can have a free involution, like translating by a two torsion element in the elliptic curve. So then there won't be any fixed set at all. So that's, or you can have, so that was the case of the free involution over here. Or you can have exactly 4 fixed points like this. So for example, an example of a holomorphic involution with 4 fixed points would just be the thing that sends each point of the elliptic curve to its negative. So then the only things that get sent back to themselves are things that are of order 2. And the two torsion subgroup of an elliptic curve is a product of, is a Klein 4 group. So they're exactly 4 fixed points. So here I've given all the 4 fixed points plus signs. Here I've given 3 of them plus signs and 1 and minus sign. And here I've given 2 pluses and 2 minuses. And then there are the anti-holomorphic involutions, and those come in 3 varieties: species 0, species 1, species 2. And in species 2, since there are 2 different connected components, you can also put opposite O-plane charges on them. And that's this case down here. So that's the sort of complete list of all the possibilities. You can, check that this exhausts all possible involutions on a elliptic curve that are either holomorphic or anti-holomorphic, together with choices of O-plane charges, etc., and choices of the B field. So one way to check the conjectures is to compute the KR groups for all 10 of these theories and show that they match up. So that's what we did. And you want the KR groups to match up. And but as I said, in some cases you have O- planes. In other words, so you have components of the fixed set for the involution where you attach a kind of quaternionic structure rather than a real structure. And so that involves twisting the KR groups, and twistings of KR are defined by what Mutuwu called the Brouwer group of real continuous trace algebras. So that turns out to look like this. So this first thing over here is the group of possible sign choices, and the second thing over here is the set of possible B fields. So notice the H2 here. And this is computed as a certain sheaf cohomology group. Okay, so you can go ahead and compute these Brouwer groups for all possible involutions on the torus, and then that's what gives you that list that we had on the previous page. Okay, so here I'm going to give you the list of all the KR groups for all the holomorphic and anti-holomorphic involutions on an elliptic curve. So I'll list them by type, fixed set, the real space in the notation of a TIA, and then the appropriate KR groups. And there's going to be some color coding in the KR groups, which you'll see in a moment. So the type 2B theories look like this. Fixed set, all of T2 means trivial involution. So this is trivial involution with a non-trivial B field, trivial involution with a trivial B field. So that as a real space, that means your torus is just S20 cross S20. S20, remember, is a circle with trivial action. Just a product of 2 circles with trivial action. And these are the KR groups that you get when you do the calculation. This is what comes out. This is the case of an involution with 4 fixed points, and then you have various possibilities for the O-plane charges. And that gives you these 3 things over here, or there could be a free involution. So then your real space is S20 cross S02. S02 is the circle with the antipodal action. And then the KR groups that you get look like this. Now, notice the way I've color-coded things. The groups that have the same color are basically isomorphic to each other except for a degree shift. So this is isomorphic to this except for a degree shift by 2. This is isomorphic to this except for a degree shift by 2. And this is isomorphic to this except for a degree shift by 2. See that?
Mhm.
And that's consistent with the 2B part of this list over here. That this should match with this should match with this should match with this. Okay, and now the 2A theories also work out similarly. So that means 2A theory is a theory with an anti-holomorphic involution. So the fixed set is either empty, single circle, or 2 circles. When there are 2 circles, there are 2 possible choices of O-plane charges. And here's the list of all the things you can get. And notice, sure enough, all the theories with the same color coding all turn out to be isomorphic except for a degree shift. So that seems to be very convincing evidence for the physicist's conjecture. So the physicists, remember, had just argued using physical T-duality arguments that these things should match up into groups according to those color codings, but they didn't compute any invariants that would show that these things have to match. Anyway, so this is what comes out. And if you wanted, you could also add a 4th family, which is the case of ordinary type 2A or type 2B string theory with no Orientifold structure. So and complex K theory. So that's just the same thing as the Orientifold theory on a disjoint union of 2 elliptic curves where the involution interchanges the 2 copies. And then you just get the ordinary K theory of the torus, complex K theory. Now, one thing we haven't explained yet is how do you set up the isomorphisms between these KR groups? You want to know not just that these things are isomorphic as abstract groups, but that there are explicit isomorphisms between them that are sort of compatible with the dualities that you expect in physics. So I set out to try to analyze that, and it turns out that all of the KR theory isomorphisms in the table come from various cases of the Baum-Kahn conjecture for solvable groups. So this was in a paper of mine in the Journal of Geometry and Physics. And let me show you some of these examples, because these are sort of very curious applications of Baum-Kahn, which I don't think you would expect, just if you weren't really looking for them. So here's so some of these examples, by the way, just come from those examples that I already talked about for over here. We have this example about this case over here. So this was the duality between S02 and S11 plus minus, this theory over here. And now if you take this duality and you cross with another circle, then you'll get one of these dualities, namely the one between this theory over here, the 2B theory with 2 pluses and 2 minuses, and the theory with the free involution. So this isomorphism over here just comes from that other isomorphism that I already told you about. But we can explain all the other isomorphisms also. And here's the most subtle of them all. So this is a really curious one. So we want a duality between the twisted type 1 theory with non-trivial B field and the theory associated to a free anti-holomorphic involution. And the isomorphism of the KR groups. All right, so this is the twisted type 1 theory with non-trivial B field. So that's this theory over here. That corresponds to this line of the table. And we want the duality between that and this theory over here. Or this one. So all three of these things should give the same groups. So here's how you get it. So let's start with a commutative C-star algebra A. Well, it's almost commutative. It's commutative up to Morita equivalence, but it's not commutative. It's the continuous functions on the circle with values in the 2x2 real matrices. And then let's give it an automorphism where you take a function here. It's a function on S1 with values in 2x2 matrices, and the involution conjugates by this, but with a square root. Now, at first sight, this R of z to the 1/2 is not well defined because a point on the circle has two square roots, but they differ by a minus sign. So the minus signs cancel out when you do the conjugation. So this thing turns out to be well defined. So there's an automorphism theta that's given by that formula. And then when you take the cross product of this algebra by the integers using that automorphism, you get something Morita equivalent to the continuous functions on T2, which are where when you apply an orientation reversing involution on T2 without fixed points, the function gets sent to its conjugate. So this is this is actually a commutative real C-star algebra, but it's not of the form just continuous functions on a space, because you have this non-trivial behavior under complex conjugation. So, and that's what this is up to Morita equivalence. Okay, actually, the actual algebra is non-commutative, but this is what it's Morita equivalent to. So now you get a duality that arises as follows. The first duality from K theory of T2 with this non-trivial B field, you have an isomorphism between this and this this cross product over here. And then you can rewrite this using this observation here. You can rewrite this as this. And then you can move the A to the opposite side by non-commutative Poincare duality. So that's this duality that was that you can find in Kasparov's papers on foundations of KK theory. And then you take this thing and apply Baum-Kahn with coefficients for the action of Z on here. And then you use the Moridi equivalence isomorphism and then putting everything together. So the whole bunch of different dualities here. Non-commutative Poincare duality used twice, Baum-Kahn and Moridi equivalence, a whole bunch of different things. So basically a hodgepodge of all the sort of standard constructions from non-commutative geometry that you know of that give isomorphisms of K groups. When you patch all those together, that gives you this duality, which is exactly what you wanted.
Can you remind me what A is?
So A was,
Oh, yeah, okay.
yeah, functions on the circle with values in 2x2 matrices.
Yes.
So it looks very close to being commutative, but not quite. Okay. And that this slight non-commutativity is kind of essential in order to get this this isomorphism over here. Okay. So, and in the same paper, I showed that all those other isomorphisms in the table, they all arise by similar kinds of patchings of Baum-Kahn with Poincare duality and a few other things. This was the most complicated example, but there are several other examples too. So now here's another kind of situation which wasn't in that paper. Suppose you consider Orientifold theories not on a curve of genus 1, but a curve of genus 0. So in other words, on CP1, the Riemann sphere. Now this thing's not a Calabi-Yau manifold, so it's not usually used as the target space for string theories, but it does arise in physics since there's a variant of string theory which is called F theory that commonly deals with elliptic fibrations from a Calabi-Yau down to projective space. So let's say, for example, for X to be a K3 surface, which is a two-dimensional simply connected Calabi-Yau down to CP1. So this thing's called an elliptic fibration if this is a holomorphic map from X to CP1 and the generic fibers are elliptic curves. And since F theory deals with these elliptic fibrations that have CP1 as the base, it's sort of natural to look at Orientifold theories that are based on involutions on P1. And then you can try to extend these to F theory by putting an involution on X to make this whole situation equivariant. And I'm working on that right now with Chuck Duran, Andreas Malmadir, and Stefan Mendes-Diaz, and I'll tell you a little bit about that in a moment. But first, let's talk about P1. Okay, so P1's a little easier. So it's easy to classify all the holomorphic and anti-holomorphic involutions on P1, right? Because any holomorphic self-map of P1 is given by a linear fractional transformation. And you just have to see which one of those, have period 2. And all the anti-holomorphic involutions you can easily check are given by a very small number of possibilities. So this is the sort of complete list of all the possible theories. So there's a 2B theory where the involution is trivial, the B field is trivial. There's a 2B theory with the trivial involution and non-trivial B field. There's a 2A theory with species 0. In other words, you have an anti-holomorphic involution that's free. So an example of such a thing would be if you send z in P1 to -1 over z bar, then there can't be any fixed points, because if there were, then z times z bar would be -1, which means z would have imaginary absolute value, and that can't happen. And then there's the 2A theory with species 1. So just like z goes to z bar. And then there's two other theories here with non-trivial holomorphic involutions, one with two fixed points, both with a plus, and one with two fixed points, one with a plus, one with a minus. So, so you see four different theories here. And with these, you don't find any non-trivial dualities, but there are two non-trivial dualities over here. So there's a duality between this and a duality between this and this. And here are the KR calculations. So this is sort of similar to what we did with the case of the elliptic curve. This is the complete list of the KR groups you can get. If you have P1 with trivial involution, then of course the KR groups are just the KO groups of S2. Here you get the KR groups of the KO groups of S2, but with a twist given by the B field, and then it turns out what you get is complex K theory. And then
But complex K theory of what?
Sorry, what?
A complex K theory of what? I'm a bit confused.
Of a point.
Of a point, okay.
Yes. So KO of S2 and complex K theory of a point, after you get rid of the two torsion, these things are isomorphic. But without the two torsion, they're not this. But the two torsion is different. This doesn't have any torsion, this does.
Okay.
And similarly here and here and here. This is, again, if you get rid of all the torsion everywhere, then all these groups look the same. But when you take the torsion into account, they're all different. So in each color code. So this is KO plus KO. KO just means KO of a point. And this is KO plus KSP. So these are all the things that you get. And again, you can ask, well, where does the isomorphism come from between this and this, or between this and this? So you can't get them directly out of Baum-Kahn because there's no group that's sort of attached to S2. But you can get them out of the dualities for an elliptic curve as follows. So we have one duality over here like this, and one like this. And you get those by pulling back the corresponding dualities for the elliptic curve. One of them looks like this, and one of them looks like this. And you pull them back using an equivariant map from the torus to the circle, torus to the two-sphere. So remember, you have maps of non-trivial degree from the torus to the sphere, but not in the other direction. So you can't map the sphere to the torus, but you can map the torus to the sphere non-trivially. And you can do that in a way that's equivariant with respect to the involution, both for the, this is the case of the trivial involution, there's nothing to do, but over here, you can make them equivariant for all these, the involutions that are indicated here. And then using these equivariant maps, you take these dualities for the elliptic curve, and then you pull them back to the sphere, and that gives you these dualities over here. So once again, the dualities that you want all arise not quite from Baum-Kahn, but I think in the abstract, I said all the dualities arise from standard constructions in non-commutative geometry. And I think that's still a fair statement, even though you need a little bit more than Baum-Kahn. You need Baum-Kahn plus, okay, a few other things.
May I ask a question about these suitable equivariant maps?
Right.
Well, I mean, everybody knows that when you have appropriate mapping of a two torus to a sphere, and then you can pull back the bot generator on a stool to become the non-trivial generator in K0 of a two torus. Is
Right.
the same true about these maps?
Yeah, but you have to watch out for the involution. So, you know,
That's what I guess equivariant refers to, right?
yes, right. Yes. Everything has to be equivariant for the involutions.
But if I forget involution and look at it as a nice continuous map, that will be the map that will pull back bot into the non-trivial generator.
Right. Yes. Yeah.
Okay.
Yeah.
Okay.
But you have to do that in a way that's equivariant.
Sure,
Otherwise, that won't help you for the KR groups.
Sure.
Yeah.
Just by the way question.
Yeah, and you can see over here, in this case, you had on the torus, you had 4 O-planes with charges plus, 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 minus. On the sphere, you just have 2 O-planes with charges plus and minus. So you have to do it in such a way that all the pluses go to the plus and the minus goes to the minus in order to get this everything to match up. So it's a little tricky, but you can do it. Now let me just say a little bit about duality on K3s, and I guess I'll conclude with that. So let's take these elliptic curve dualities and P1 dualities, and out of those we can construct a duality for theories on a K3 surface. So once again, I'll remind you a K3 surface is a simply connected Calabi-Yau manifold with closed Calabi-Yau manifold with complex dimension 2. So it's a you can get such a thing as a quartic surface in P3, or you can get, I mean, K3 surfaces are all diffeomorphic to each other. There are lots of different isomorphism classes, but they are all diffeomorphic. They all have Euler characteristic 24, and they have cohomology in exactly dimensions 0, 2, and 4. Of course, it's one-dimensional in dimension 0 and 4, and then the second Betti number is always 22, and the intersection form on the middle cohomology looks like 2 copies of the E8, 2 copies of the E8 form together with 3 hyperbolic planes. Okay, so these have very rich geometry. There's a lot known about them. And here's one way to get them. So let's take 2 elliptic curves, E1 and E2. And you can construct what's called the Kummer surface out of them by doing the following. So first you take E1 cross E2, and you divide out by the involution that sends xy to minus x minus y. So in other words, you just multiply, it's just the involution is just multiplication by -1 on both factors. So that this involution is free except for 16 fixed points. The fixed points are the 2 torsion points in both factors. So E1 has 4 2 torsion points, E2 has 4 2 torsion points. So together you have 16 2 torsion points in the product. So they're going to be 16 singular points where and then you blow up these 16 singular points, and that gives you a non-singular K3 surface, turns out. And it has a natural projection down to P1, where you identify P1 with E2 divided out by this involution multiplication by -1. And there are several choices of involutions on E1 and E2. In this case, since K3 surfaces are indecomposable, you want both involutions to be holomorphic or both of them to be anti-holomorphic. It doesn't really matter which you do. But you choose involutions such that the product of the involutions commutes with multiplication by -1. There are lots of choices where that happens. And then you get an involution on X that's compatible with this projection down to P1. And then you apply those dualities that we talked about for elliptic curves fiber-wise. So to the fibers of this elliptic fibration down to P1. And so the fibers, remember, elliptic curves, think of those as little tori. You do one of these dualities on each one of these fibers with respect to one of these involutions, iota 1. And then putting everything together, you get a duality between X and this involution to another K3 with another involution. Patching all these isomorphisms together, you'll get again, isomorphism of KR theories between these two things. So this is an example of duality on K3 surfaces, about which, as I said before, quite a bit is known. So I don't think these dualities are really new, but this particular way of sort of analyzing this. Okay, so I guess that's pretty much what I wanted to talk about. So why don't I stop here and open it up for questions.
Thank you very much. Okay, guys, fire at will. Tomek, Adam, Tomek. But you have to unmute yourself.
Yes, thank you. I have a question.
Sure.
So probably physicists' argument is based on some physical principle.
Right.
And probably this principle is some general principle. In your explanations for these isomorphisms,
Yeah.
you are mixing many arguments.
Right.
There is no one unifying principle to find these isomorphisms. Is there some conjecture for some mathematical unifying principle to get all these isomorphisms, parallel to probably some unique physical theory explaining them all?
I unfortunately don't know of any simple way to do it all in out of a single principle. The only way I know how to construct these isomorphisms is to patch together various kinds of things that were known. I mean, that's a very good question, but I don't really have a good answer for it.
But what is this unifying physics principle?
Well, I wouldn't say there's, I mean, and if you look at the physics papers, there's no single principle either. There are, again, a collection of various arguments, which are in many cases rather ad hoc. They say, well, consider, collapsing this circle to a point and then blowing this thing up. And then, you expect the field to concentrate in this place and that sort of thing. So they're kind of heuristic arguments. I'm not sure that you can pin those down very clearly either.
That's what I expected.
Yeah, I mean, you can try looking at the physics papers and see if you can make more sense of them than I could, but that's about the most that I could
Yeah, but at least
figure out
this,
from reading them. Yeah.
at least this mirror symmetry has some organizing principle.
Yes, but even there, it's a little bit tricky because not mirror symmetry is not quite a it's not quite a bijection. It's so not every string theory has a unique mirror. Sometimes there's more than one, sometimes there isn't one. It's generically one-to-one, but you know, sometimes there are little exceptions where it doesn't quite work and so on. So again, I don't, you know, you have to give kind of ad hoc arguments for what to do in those other cases. So
So if I remember well, they are working with duality of families.
that's right. Yeah.
So I wonder if generic members of these families have the same topological type.
Well, the
I'm not
topological type, I mean, it depends what kind of mirror symmetry you're talking about. If you're talking about mirror symmetry for threefolds, yes, then the topological type can vary, but in a single family, it's all constant. If for K3 surfaces, all of them have the same topological type, and the difference is all in the complex geometry. There's another special feature of K3 surfaces, which I didn't mention, but makes them particularly curious examples, and that is that they're hyperkähler, so that basically any anti-holomorphic involution on a K3 can be viewed as a holomorphic involution for a different complex structure on the same manifold.
Mm-hmm. Yeah. Is it responsible for appearance of this quaternionic structure?
Not entirely, because those showed up even in the non-hyperkähler situation with the elliptic curve. So.
Okay, thank you.
Mm-hmm.
And okay, Adam, go ahead.
So at the beginning of your talk, you mentioned that this anomaly constellations happens in dimension 10. That in fact it forces dimension to be 10. But as far as I know, originally string theory was formulated in even higher dimension, 26.
Yeah, that's the non-supersymmetric version of it. Yeah, or just yeah, that's the bosonic string. The non-supersymmetric bosonic string is in dimension 26. Yeah.
And sorry, is it somehow related? The fact you mentioned at the end of your talk that some Betti numbers of some surface was equal to 22. So 22 plus
no, it's well, yeah. So K3 surfaces have Euler characteristic 24. That's just the way it turns out.
So it
I don't
has
think
nothing
that
to
number
do
has
with
anything to do with that other number. No.
Okay.
Yeah.
Okay. Thank you.
Anybody else? I think Richard is eager to ask a question.
No, not this time. Thank you.
No.
Thank you for the talk, Jonathan.
Okay.
Sorry, maybe one more question. So in standard quantum field theory, when you deal with a free field, you deal with a Fock space constructed from a Hilbert space, and there is a bosonic version and fermionic version of this Fock space.
Right.
And is somehow this supersymmetry related to the fact that you consider some isomorphism between these two Fock spaces, or it is in a different flavor?
Well, there is an isomorphism between them, but the supersymmetry amounts to more than that. So basically, I think a better way to think about supersymmetry just in a kind of free theory is that it sort of blends together the Poincare group, which is the usual symmetry of free fields in Minkowski space with something that takes the fermions into account as well. Or to put it this way, so the supersymmetry gives you a way of it sort of forces every boson to match up with a fermion. And that's a very rigid kind of structure, which imposes a lot of extra constraints and makes it easier to do calculations. Now, admittedly, there's not much in the way of experimental evidence for supersymmetry. We haven't really detected it even in the LHC yet. So it may be that it really doesn't exist, but it seems it's such a nice mathematical construct, and it can be used for so many things in mathematics that there probably is some version of it in some part of the real world, but we just haven't found it yet.
Yeah. Okay. If it's beautiful, it must exist. Okay.
Oh, I think that there were high hopes to find supersymmetry in the early experiments in LHC, but
Yeah, it could be that it just
Somehow-
requires much too high an energy. Right.
Okay, thank you.
Yeah.
Anybody else? Ludwig? Hello, Fiesta? No. All right. So if there are no further questions, let us ask Jonathan again and stop recording. Thank you so much.
Okay, thanks all of you.
Our pleasure.